Hi everyone. I figured I'd throw together a quick video just to review some of the content you've been working on in class. Let's get started. Obviously, you've been working on this theory called plate tectonics, which is basically an extension of Alfred Wegener's work. This theory that we're going to look at was put together in the mid-1900s and built upon what Wegener began working early in the century. So let's get started. The first thing we need to know is this. The outer shell of the Earth, which I gave an example of being the magic shell on a scoop of ice cream, this solid outer crust of the Earth, we call it the lithosphere. It's actually broken into pieces that we call plates. You see them here. You can call them lithospheric plates, you can call them tectonic plates, or simply plates. But this is the solid outer part of the Earth that we live on. Some of the plates are all oceanic crust, some of them are all continental, and some are a combination of the two. That's going to become important. Keep in mind that we do have these two distinct types of crust. If you look at the gray here, this is our continental crust. It's thick, it's made of the rock granite, it's not quite that dense, only about 2.7 grams per cubic centimeter. But if you look at the dark gray area under the oceans, that's the oceanic crust. It's very different. It's much thinner, more dense because it's made of the rock basalt. The density of the basalt is about 3 grams per cubic centimeter. Keep in mind that information can be found on your Earth's interior chart in your reference tables. Now, that crust, whether it's oceanic or continental, along with this kind of orangey section called the rigid mantle, those two together are what make up our lithosphere, this solid outer shell of the Earth. Keep in mind that beneath that is kind of a gooey, plastic, partially melted bubblegum layer called the asthenosphere. And so the plates that we live on are actually floating on the asthenosphere beneath. Now down in the asthenosphere, that melty, gooey, bubblegum-like rock is actually able to move. And it moves because of a process known as convection. Essentially, convection says that hot material becomes less dense and rises. And then when it rises, it cools down, becomes more dense, and sinks. And what we end up with are these rising and sinking currents called convection cells in the mantle. Those end up being the machine, the force that is driving the motion of the plates. So in this diagram, we have a type of boundary called a divergent boundary, where the plates are literally being ripped apart by the movement of the convection beneath. Keep in mind, this convection takes place in the asthenosphere, right below the lithosphere. So let's take a look at a map of the plates. Okay, there's a very similar map in your reference table, which we'll see shortly. But for the moment, take a look. You notice that the plates, some are very large, some are a little bit smaller, but they're all moving. And what that means is that there's lots of action at the places where plates meet. For example, that's where we find all our earthquakes, shown here with pink dots. That's where we find all our volcanoes, shown here with red triangles. And this is also where we find a lot of the Earth's active mountain ranges. So keep in mind that all seismic activity, earthquakes, volcanoes, and mountains, tends to happen at or near these boundaries between plates. Which brings us to those boundaries themselves. Now, all of plate tectonics comes down to the fact that things happen when two plates interact with one another. So we need to know what those interactions look like. And it really boils down to three types of interactions, three types of plate boundaries. The first is known as a transform boundary, and that occurs when plates slide past one another, as seen by these arrows. We also have convergent boundaries, where plates collide, and divergent boundaries, where they drift apart. You should be familiar with each of these and the kinds of things we see at each of them. So let's go into some examples here. Okay, I'm going to be alluding back to this chart. This is a map in your reference tables that shows plate boundaries. So keep that handy as you're continuing to learn about this. Let's start with transform boundaries. So these are the boundaries where plates slide past one another. If you take a look at this animation, you'll notice the lithosphere, floating on top of the asthenosphere, is being driven by convection currents, which is causing them to slide laterally past each other, right past each other. And so right along that boundary in the middle, you get a lot of pressure built up, a lot of grinding of the plates, which is often released in the form of earthquakes. Transform boundaries very commonly have earthquakes. However, they don't tend to have volcanoes, they don't tend to have major mountain ranges, and certainly not trenches. The only real feature we see at transform boundaries are earthquakes. This is an example of a place on Earth where you can actually see a transform boundary at the surface. This is known as the San Andreas Fault, and it's found in California. It's responsible for the big earthquake risk of cities like San Francisco and LA. Let's go back to our reference table for a minute here and see that the transform boundaries are shown down on the bottom with this symbol, shown in green here. There's a couple of them, not too many, but the most famous and important one would be the San Andreas Fault, shown right there. Again, if you forget how transform boundaries actually work, the arrows kind of reveal the motion, so it's a good tool to use your reference tables. Next type of plate boundary would be convergent boundaries. Now, these are a little more tricky because we have to consider not only the fact that two plates are coming together and colliding, but what type of crust is involved. For example, we see different things happening when it's oceanic crust colliding with oceanic crust, as opposed to when it's continental colliding with continental, and so forth. And so we have a few different types of convergent boundaries. The first type we call a subduction zone, and as you can tell by this little animation here, this happens when continental crust on the left collides with oceanic crust on the right. Now notice that the oceanic crust is sinking underneath the continental crust, and that's because oceanic crust is more dense than continental crust. It's heavier. And so when the two collide, the heavier oceanic crust sinks underneath the lighter continental crust. When it sinks, it melts because it's hot down in the asthenosphere. And that melting rock finds little cracks and crevices to rise through and ultimately erupts at the surface, forming active volcanoes. So some of the features we look for at subduction zones are a chain of tall mountains and active volcanoes, a deep ocean trench seen by this dark line just off the coast, as well as lots and lots of earthquakes, which tend to happen along that subducting plate. We also have island arcs. Now, very similar to a subduction zone. The only difference is that this is oceanic to oceanic, so no continents involved here. The one thing that's tricky is it's a little hard to tell which plate is going to subduct, being that they both have the same density. But eventually one plate, usually the older rock, will sink under the younger rock. And again, we will get this melting, which causes rising magma to create active volcanoes, which in this case form islands, volcanic islands, because we're talking about areas out in the middle of the ocean here. We also get a trench, which you can see clearly in the water there. And of course, we get lots of active earthquakes along the subducting plate. Before I go back to the chart here, we also have a third type of convergent boundary called a collision zone, and that would be continental to continental. The best example of that would be India crashing into the Eurasian plate, where the Himalayas are forming. But again, convergent boundaries can be seen with this symbol down here. And probably the most famous one that we will discuss is the Peru-Chile Trench on the west coast of South America. So that would be an example of a subduction zone, because you notice the Nazca Plate is in the ocean, so that's oceanic crust. The South American plate is a continent, that's continental crust, and so that gives us a subduction zone. That's where the Andes Mountains are, lots of volcanoes, lots of earthquakes. Finally, we have divergent boundaries where different plates drift away from each other. Again, we want to consider the type of crust involved. So if it happens on land, we have what's called a rift zone, where the land actually rips apart into two. We see this happening in Eastern Africa right now at an area known as the East African Rift Zone. As you can imagine, when the rock rips apart, it allows magma to escape. So we get active volcanoes. We do get some minor earthquakes here, though they're not as significant as the convergent boundaries would be. Often we will see this out in the middle of the ocean, and we call that a mid-ocean ridge, shown here. So the convection currents are actually pulling the plates apart. The magma is coming up in the middle, forming mountains and volcanoes, and again, some earthquakes. Now there's one tricky thing of this, or actually a couple tricky kind of points here. One is not too bad, and that's the idea that the younger rock is always going to be found right along the ridge, because that's where all this magma is cooling to form new rock. As you get further away from the ridge, the rock age will increase. It gets older and older and older as you get further from the ridge. Now, here's the trickier thing. This rock, when it forms, it actually records the Earth's magnetism. If you recall, we talked about how the Earth is like a giant magnet. But that magnetism changes every so often. And so those changes are recorded in the rock. And so what we see in the rock on either side of a mid-ocean ridge are these alternating bands of magnetism which match up on either side. And that's an important observation because it proves that the rock is actually spreading apart, and it proves that the divergence is actually taking place. So if we look at our reference table, here's the symbol for divergent boundaries. And again, the most common one is probably the one that spans the Atlantic Ocean, the Mid-Atlantic Ridge, right through here. It actually extends all the way down south. But that's probably the best example, although you see them all throughout the oceans of the world. Now, we do have one problem here because plate tectonics says that all volcanoes and earthquakes should happen at these plate boundaries. But if you really look at the Earth carefully, there's a handful of places where we get volcanoes that are not at a plate boundary. And the best example I could give would be Hawaii, smack in the middle of the Pacific Plate. And so geologists had to consider this and come up with an explanation as to why we had some volcanoes that weren't at plate boundaries. And the answer is that these locations are hotspots. So a hotspot is simply an area where we have a single area of magma that's able to punch through in the middle of a plate. So we're not talking about a boundary here. We're talking about one simple individual solitary point where you have active magma rising up, and it rises from something called a plume. We can't predict where these will happen. We notice there's maybe a dozen of them on Earth right now. Sometimes they're very active, sometimes they're not as active. Here's how they work. If you look at this diagram, you're going to notice shortly a mantle plume, there it is, coming up from the asthenosphere. It's just a hot spot. And that magma is strong enough to actually punch through the lithosphere to create an active volcano. But the problem is the lithosphere is moving, because remember, all the plates are constantly moving around. And so you'll get this active volcano, which is then dragged to the side, making way for a new active volcano to form. And then that is dragged to the side, and a new one will form, and so forth. And so what you end up with is this chain of islands, if it's happening in the ocean, with one active volcano over the hotspot, and then a chain of extinct or dormant, not active volcanoes extending away from it. And what's cool about this is if you look at where the extinct volcanoes are, they tell you the direction that the plate is moving. So that's pretty much in a nutshell the content that we need to know about for this chapter. You guys will be learning a lot more about it in class coming up, but I just wanted to do a quick overview for you. Thanks a lot.